So I think I'll give a different flavor talk that will come from a more technical perspective, but I'll try to tie it into some of the issues that have been talked about today. And first, a little bit of color, additional color to my background. So in addition to being academic, I actually spent a few years on sabbatical in a startup, Argo AI. So that was focused on self-driving vehicles, and specifically perception for self-driving vehicles. So I can relay a bit of my own experiences of the types of problems that I thought ended up being really important, and that might have been difficult than some of the technical challenges that I historically worked on. And I should also just give a sort of a side note that it's the computer vision group at CMU is a very long-standing group. It's actually celebrating its 50th year of inception, and there's actually a reunion that's happening upstairs right now. So there's quite a few of legendary stalwarts that are walking around this building. So I'm going to view myself as an ambassador here and just give a little bit of a flavor of the recent innovations in this space, and maybe my own personal take on where some of these challenges and potential opportunities lie. Okay. All right, so first, so I'm going to look at the challenge of computer vision. So what is computer vision? It's really this challenge of, given visual imagery, can you build algorithms to understand what's happening there? And I'm going to look at this challenge through the lens of self-driving vehicles. And so I want to first point out, I want to first pose this question, which is, given this incredible progress that we're seeing in AI, I'm sure all of you have used ChatGPT and sort of have a firsthand sense of the incredible things it can do. Why hasn't that translated to self-driving vehicles? I would argue that that still hasn't really been a successful business use case yet. No one's turned a profit. The company that I was at, the startup that I was at, folded last November. So in some sense, that was not a successful venture. So why, given all this incredible innovation, why is it not translating to that space? And that's really what this talk is going to be about. And one of the peculiar things about working in this space, okay, is that there's a lot of federal oversight. So I'm sure all of you have seen as well, there's very famous failure cases of crashes and kind of failures of the tech working. And what I'm showing now is a particularly well-documented one. Because when you test these systems in real roads, that requires incredible amounts of oversight, including at the federal level. Every crash that happens, there's actually a National Transportation Safety Board analysis. So you can go online and look at this pretty involved document about the failure that occurred. And this is a well-known one that was actually a fatality. So there was a self-driving vehicle that had a safety driver in it. There was a pedestrian walking across the road with a bicycle. And unfortunately, the vehicle didn't stop in time, and the pedestrian died. So it's an incredibly sort of tragic and solemn event. You can look at this, which bears a whole sort of a bunch of reflection that's required because of it. And so you can sort of dive into this safety analysis. And I should point out that it points out that there's failures at many levels, from improper training of the safety driver, all the way to sort of technical failures. And so what I'm going to focus on, wearing my academic hat, are what were the computer vision failures that caused this to happen. And I find this fascinating because I've never seen sort of the work that I do, or the space that I play in, talked about in this way. So what it gives is a pretty detailed analysis of what the brains, the software stack, was thinking up until the point of impact, from t-5 seconds to t-1 second. And you can see it would sort of flash between different classifications of what it thought this person was as they were walking across with a red bicycle in hand. Let me just sort of read it out. The automatic driving system changed pedestrians' classification several times, alternating between vehicle, bicycle, and other. And because the system never classified the pedestrian as such, the system's design excluded tracking history for non-persisting objects, those with changed classifications, and was unable to correctly predict the pedestrian's path. And so what I look at this as is that in some ways, it actually is a pretty hard challenge of what you're trying to do is build a stable interpretation of what's happening in the world. And if the world was not changing, this would actually be much easier. And that's actually a classic problem in our field, sometimes called structure for motion, or simultaneous localization and mapping. But the difficulty is that if the world is changing, it's almost a moving target. And the example I always give is, imagine you're driving by, and you might even have this scenario something similar to this when you're driving, when then your line of sight is occluded. There's a big bus somewhere, and you don't quite know if what's on the other side. And it's possible that as you're driving, maybe a child walks out from behind that bus, and so a split second ago you didn't see someone in front of you, and now a split second later you do, and you have to make a call very quickly. Is this change that I see, is this a flicker? Is this a noise in my measurement process? Or is this an actual change in the environment? And you have to make this decision very quickly and then sort of decide if you're going to perform an evasive maneuver. You know, slamming on the brakes is also dangerous. So you have to sort of examine these trade-offs. So fundamentally, the technical challenge that I saw was that it's really hard to build stable interpretations of a dynamic world. It's almost an oxymoron. Another reaction I oftentimes get when I show this is, why does this system care if it was a person or a vehicle or a bicycle? If you see something there, you should stop. And I totally agree with that as well. I almost feel like there's been this overemphasis on what I would call semantic recognition or semantic classification, trying to name things. And instead, at a much more basic level, we should just know where things are and where they're moving. You know, it doesn't matter what it's called. And so you can see many of these examples even on YouTube. So perhaps the most widely deployed system is Tesla's, which we can have conversations about if that's really self-driving, if it should be marketed as such. But in any case, here's a case of a horse-drawn carriage that the system gets confused about. It clearly doesn't know what it is, and it also changes its classification. And once again, I would argue, why is it even, you should just try to figure out what's there and how is it moving. And that's the important question to answer in terms of how it can safely navigate. Okay. So the argument that I'm going to kind of tie this to is I'm going to try to link two different paths forward. And so one is this notion of like foundational data-driven learning. And this is most viscerally manifested in large language models, so things that you guys have used, ChatGPT. So there's amazing things that can be learned when you try to learn patterns from data at scale. But those patterns are learned on linguistic data, words that have been typed into text. And instead, I'm going to argue that we kind of need that kind of foundational knowledge, but somehow tied to the real physical world that we're in. You know, our world is three-dimensional, and if you want to think about it, it's actually four-dimensional if you think of the fourth dimension as time, because of this time-varying aspect that I think is really important. So I think of, you know, I wouldn't call myself a language person, so a vision person lives in the right-hand space. So you can imagine there's innovations that may not have been talked about in the world of like virtual spatial understanding. Maybe this is most viscerally seen in things like metaverse, building a virtual space that's 3D that you can move around. So I'm going to try to argue that we actually need technology to try to combine these two sort of disparate views of large foundational models that can be learned from text, and this more kind of 3D, 4D spatial models that ground the ground knowledge in the physical world. And the way we're going to try to do this is essentially, instead of trying to learn patterns from text, let's try to learn patterns from physical data, from videos. And you can imagine here, you know, these just videos you get on YouTube or videos you see in webcams actually display an incredible amount of structure about the world. You can tell there's a three-dimensional world here. You can tell it's a dynamic world as it moves around. And we can almost try to apply some of these techniques that have been used for learning large language models to these kinds of data, which I argue is almost just as available. You know, there's plenty of cameras. We all have cameras in our back pocket. We all have security camera footage that is widely available. And so I should also mention that this view of foundational knowledge that's more tied to like sensory measurements of things that can be seen by cameras has also been advocated by many. Maybe one of the more well-known advocates is Yann LeCun, who is one of the, let's say, the godfathers of deep learning. You know, one of the harbingers of large language models. But there's this push of, okay, we need to tie this more to physical sensations and physical measurements that we measure. Okay, so I'm going to sort of give you a kind of a path forward in this direction. Okay, and maybe another analogy that I'll give here is that while people talk about intelligence, you know, there's this sort of philosophical questions of to what degree are chatbots intelligent, which I won't sort of bother throwing my head in that ring. But the question I'm more interested in is actually building a different kind of intelligence. I would love to build a system that could basically be intelligent as my dog, or a fruit fly, because those things can navigate. I don't think those things would have the errors that I just showed you in the first couple of slides. So and clearly those things don't learn their knowledge from reading the Wikipedia pages. It's not linguistic. It's more tied to the world. So that's the goal that we're going to try to sort of talk through the next few slides. And if you apply this more kind of biologically motivated view of intelligence, one thing that becomes clear if you open up your neuroscience textbook is that motion plays a huge role in how flies and dogs move around and navigate. And so what we've been working on in our lab are sort of techniques that sort of use motion and pixel motion as a first-class citizen. So what they do is, given a video stream, you first try to understand, answer the simple question. Every pixel, I want to compute an arrow that says where is it moving to in the next frame. And the hypothesis is that if you do that, it turns out you can actually impute a lot of things about the physical world. You can tell when you're going to hit something because as you're moving toward a wall, you'll see this expansion. And so one of the things that we've used are neural networks that have been trained originally for things like image recognition. It turns out you can take all that technology and repurpose them for this, what I would call a lower level task, which is identify the motion of every pixel. And if you do this, you can now try to build systems that I think are more robust, that can understand where things are and how they're moving in the world. And I'll sort of show one technique for doing so. And that is, the technique for doing so is something called inverse graphics. And this is interesting because the actual technique doesn't really require large-scale data. So it's a very different, it's sort of a very different approach than what you normally might be thinking of with machine learning. And that is, if you're a computer graphics engineer, there's a very intimate relationship between computer vision and computer graphics. If you're a computer graphics, I should say animation engineer, and you work at Pixar, your lifeblood is solving this forward rendering problem. And what that is you construct a virtual world where you put shapes and objects and light sources, and then you press a render button, which essentially simulates a little bit of physics, and it creates a virtual image. So, and this is why, animation has had incredible advances in special effects, et cetera, where you can make that virtual image look more and more realistic. You can think of computer vision as solving the inverse problem. We're given the image, and we're trying to figure out what are all the shapes and light sources and all the stuff in the world that generated that image. And this has been a very classic way of thinking about computer vision, which is you make a guess at what's happening in the world, and you basically push your render button, the same button that someone at Pixar would push. So you can maybe guess that that you're looking at a video of a circle, of a sphere, and you press the render button, and then what you get out is an image of a sphere. But then that image doesn't look like the actual image that you see here. Let's just say it happens to be a camel. But then what you can do is you can essentially phrase this as an optimization problem. Let me try to search for different interpretations of my 3D world such that when I render it, it looks like the actual images that I see. And so like I said, this has been sort of proposed for decades. So the folks upstairs have introduced this notion of vision as inverse graphics about 50 years ago. But an innovation that's been happening is that this has always been hard to solve in practice. And one of the game changers has essentially been, let's see if this works. Oh, okay, this is just a video of trying to solve this problem. You keep searching for a hypothetical interpretation of a deforming scene such that when you press your render button, you generate images that look like the actual images you see in a video stream in front of you. It turns out you can phrase this as an optimization where, let me look at the difference between my rendered image and my real image, and that's my error. And now I want to try to tweak my interpretation of my 3D world to minimize that error. That optimization has been really difficult, but, oh, boo, sorry here. Ah, okay. Okay, here. So here's actually a visualization of the optimization in action. So what's happening is that it first thinks that it's a fuzzy scene. It doesn't quite know what's happening, but it keeps tweaking around what it thinks the geometry of the scene is, and eventually realizes that it's a cat that's deforming and flicking its tail. And at the same time, in order to get this right, you also have to infer where the camera is. And that's what we're seeing in that third column. It's a bird's eye view of the scene where this optimization is trying to figure out how to place cameras so as to better generate images that look like the actual images in a video stream. So the trick that sort of allowed this to happen, even though this has been around for 50 years, is that it's this kind of fortuitous serendipity that it turns out a bunch of the hardware and software designed for gradient-based neural network learning can be repurposed for this gradient-based optimization. So all the GPU hardware that we have, even the software libraries, I feel like this has also been a game changer from when I was a student to when to where my students are now, is that there's incredible software libraries that you don't have to get down to the low-level CUDA programming, which not a lot of folks have that expertise, but people have built these incredible repositories where you can build on top of them. It turns out, even though that's all been designed for learning neural networks, you can use them for solving this optimization problem of solely figuring out how to learn gradients. Sorry here. How to learn gradients, which mean how do I update my interpretation of my 3D scene to better generate a rendering that looks like my real image. So this is the most technical bit that I'll show you. And then my goal for the rest of the talk is to kind of show you some cool pictures that result from this. So what I'm showing you here is a system that does exactly this. It solves this vision as an inverse graphics problem just given a video sequence. And what it's trying to do is, given these video sequences, it's trying to come up with a hypothetical interpretation such that when I render it, it looks like the image is seen here. So what's kind of amazing about this approach is that there's no real training data. It turns out there's, the way to think about this is that you're just given, on some sense, test data, which is the frames of a video stream you're trying to analyze. And this is trying to fit an interpretation that best explains all those frames. And because of that, it doesn't suffer from the biases of training data. So one way to think about this is that right now, if you're trying to build accurate 3D models of people, the standard approach might be, let me build a huge data set of 3D scans of people. And in fact, if you're trying to build high quality body scans for, let's say, understanding how clothing can drape on people, that's actually a very successful approach. But one argument is that that's going to be really hard to build that fidelity of a data set for other kinds of objects like horses or camels or pets. And just to call out, one of the things we discovered when we were trying to deploy self-driving vehicles in Washington, D.C. is there's lots of horse-mounted police. So it turns out you do see horses running around streets. And on any typical sort of data-driven computer vision system, it's not really going to be it's not going to be trained typically on a large amount of horses. But if you take this approach of almost just trying to fit to the motion that you're seeing in the data, you can actually figure out, oh, there's something there, even though I don't know what it is. I don't know what to call it, a horse or a dog or a weird structure that's in the bottom left. But I know that there's something physically there, and I know how it's moving. Okay, so this is sort of like a little bit of a philosophy of where we came from, and I just want to show some sort of fun visuals that you can kind of construct with such systems that can understand where things are and how they're moving. Okay, I want to keep an eye on the time. I feel like I should probably be running off in a couple of minutes, but okay, I'll just show some fun examples. So one really cool thing we can do is that not only we can fit not just to image data, but to depth data. So it's something that you guys might not know, but most of you have a LiDAR sensor in your back pocket. And that's because iPhones actually have 3 of these sensors, and one of them is a LiDAR. What it does is it shines lasers out into the world, and by recording a measurement of how long it takes for the reflection to come back, it can tell the depth of the scene. So this is kind of amazing to me, and this is actually, LiDAR is the same technology that's also used in a lot of these self-driving vehicles to sort of understand spatially what's happening. So what you can do is, you can imagine what that suggests to me is that pretty soon we'll be able to collect video clips where we actually have depth recordings as well as color recordings, and that makes it even easier to do this reconstruction that I talked about. So here's an example of a video of my cat running around. And now we're going to apply this reconstruction inverse graphics algorithm to reconstruct the background, reconstruct the cat, and also reconstruct the camera of how I'm moving around. And one of the fun things you can do with this is now that you've reconstructed it, you can re-render it from a different point of view. So just from one video of a handheld scene, you can try to say, okay, what would it look like if I put a virtual camera at the top of the scene? And you have this, it's a layout of my living room with my cat moving around. You can even do something funny. You can say, what happens if I put my virtual camera in front of the cat's head? And you can look at the world through the cat's point of view. You can do something also kind of cute. You can put a virtual camera right behind the cat and sort of watch it as it's moving around. This is because you've reconstructed the motion of everything. And I'll show some of these, hopefully if this works, we'll see this video moving around. So this is kind of neat. So the claim is now you can just take your camera, take a little recording, apply these vision as inverse graphics algorithms, reconstruct the motion of how things are moving, and now that you've reconstructed the motion of how things are moving and what the 3D shapes of them are, you can re-render them from different views. Fun examples of, you can have complex scenes when there's multiple moving objects. Oh, and I'm showing that little virtual yellow camera that represents the first-person cam of what the cat sees, and the blue camera is almost like a game cam. It almost looks like if you played like a first-person shooter, that's the sensation you get. Here's some more fun examples. Okay, all right. Maybe I'll show off a couple more, and then we'll call it quits there. Okay, so some things you can do with this sort of technologies, you can, if you've reconstructed how things are moving and also understand what's moving versus what's not, you can remove objects. So that second image is kind of a fun example of, you can kind of tell the dog is reacting to someone, but we've removed the person in there. And because you've reconstructed everything, it's sort of easy to just not re-render with that object in place. Here are other fun examples of, you can do kind of augmented reality applications of put virtual sort of hats or clothing on top of people. Another fun example is you can re-render from the person's point of view, but if you really understood how everything is moving in this world, you can even re-render from this rotating ball's point of view. And you'll see that here. Okay, so sort of like fun kind of cute applications of what you can do. And hopefully this is very evocative of things that you can do in the metaverse and virtual reality. But in my view, this is also the kind of knowledge that's needed to get a self-driving car working in order to really understand where things are and where they're moving. Okay, and we've worked at doing this kind of reconstruction at scale. This is actually a construction site that's going to be, I think, a new robotics AI building in Mill 19, so down by the river. A student went and they flew around the drone, captured all these images, and they did the same thing of reconstructing a space-time reconstruction of that would, if you press the render button, generates the images. And now with this reconstruction, you can actually do virtual fly-throughs, sort of joystick control and zoom in and look at different pieces of construction or different spatial structures. Okay. You could do this at scale. We've done reconstructions of all of Pittsburgh. So you can actually fly through and look at different neighborhoods. We've taken these dynamic reconstructions and also used them to not just render cool looking stuff, but then actually drive other robots. So I think there's a lot that can be done if you kind of focus on these low level problems of understanding where things are and where they're moving. And maybe, oh, here's a fun example that another aspect of understanding how things vary over time is that it could be that the geometry doesn't change, but the actual appearance does. So it turns out if you actually collect very large scale footage on the order of hours or days or months or years, appearance changes. Snow appears, leaves turn gray, or leaves turn brown in the fall. And so it turns out that just by applying some of these same techniques of understanding space-time models of the world, you can also understand space-time models that understand how the color of things change over time. Okay, so maybe I will just skip to the end of this, because I think I am over time. Sorry here. Let me go back. All right, this thing is not listening to me now. Is it possible to, just go forward? I'm happy to sort of skip this in interest of time, and we'll just, I guess, end here. If you could just press the play again there, and we could just, close up here. So the kind of take-home message here was, from my perspective, one of the big challenges in getting vision to work for, let's say, robotics applications like self-driving vehicles is really this kind of simple problem of building stable interpretations of a dynamic world. And the path forward was essentially trying to apply these data-driven techniques people have learned people have used for text, but really do it for visual data at scale. But then the magic technical innovation that really allows this to happen was this technique of differentiable rendering that was actually been around for decades, but really hooking that up with contemporary hardware and software designed for neural network learning. And I guess I will end it there. I'm happy to take any questions.